Okay. So yesterday we talked about single replacement reactions, how one thing replaced. I'll get it for you later. Okay. But single replacements are ones that we can actually tell whether the reaction is going to happen. Okay? So with single replacement, we can tell whether the reaction is going to happen before we start. Just by looking at what you put together, you can tell what it's going to do. Okay, so we said we had a dance analogy. Okay? So in the dance analogy, single replacement was somebody coming up and tapping somebody on the shoulder and say, mind if I cut in? Okay? Well, picture this. There's an order, there's a pecking order. So if a senior taps on a freshman's shoulder, mind if I cut in? There's going to be a change. But if a freshman taps on a senior's shoulder, mind if I cut in? There's unlikely to be a change. Does that make sense? Okay. Well, that's about activity, how active they are. The senior would be more active than the freshman because the senior could replace the freshman, but the freshman couldn't replace the senior. Okay. Chemicals have that same kind of pecking order. So juniors would replace sophomores and freshmen, but seniors would replace them. Okay. Some metals are more active than others. And more active replaces less active. And there's a list on page 333. You don't have to memorize. I will always give you an activity series. I may make it. This is just a select number of metals. They actually have it for a whole bunch of metals. Which one's higher activity than the others? So I think on your homework I got a longer one. Okay. It's got more metals, but they're still in this order. Okay? You don't have to memorize it, you just have to be able to use it. Lithium's up top, it's the most active on this list. Silver's on the bottom, it's the least active on this list. Okay? And here's how they made that. Okay? And it's a lot like the lab you're going to do tomorrow. Okay. So here I have 8 solutions. Okay. They're all nitrates with different metals: magnesium, zinc, copper, silver, iron, lead, nickel, and tin. Okay. So here's a group of chemicals, and I'm going to take a piece of magnesium and stick it in. Okay. And then I can remove them, and if you'll look, that the magnesium one didn't do anything, but the zinc one's got coating, the copper one has coating, and the silver one has coating. That means magnesium was able to take the place of zinc, copper, silver. Zinc was with nitrate before, it had a partner, magnesium could push it out. But if I do zinc and do the same thing, and when I pull them out, now magnesium doesn't change, zinc doesn't change, but the copper does. So that means Magnesium is higher activity than zinc because zinc couldn't push it off. And zinc is higher than copper because it could push the copper off. The one lowest on the list always ends up by itself. The freshman always ends up dancing alone. Okay? The seniors always end up dancing with somebody. If they're by themselves, they don't end up by themselves. Okay? So what about silver? Zinc is higher on the list than silver. Now if I put silver here, and I pull them out, nobody's got any metal. That means silver wasn't able to push anything off. Silver's really low on the activity series. Okay? So that's how they make this activity series. I knew because silver couldn't push off copper, silver's lower than copper.
Are we going to have to memorize that?
I've already mentioned it twice, so go back and listen to the notes. I'll tell you, that'll tell you whether you have to memorize it or not. Okay? So, higher on the list replaces lower on the list. So if the element by itself is higher, the reaction happens. If the element by itself is lower, it doesn't happen. That the one by itself has to be strong enough to push off the one with a partner. Seniors always end up with a partner. Freshmen always end up alone. And this would be important to know. I mean, if you're making a boat out of metal, wouldn't it be nice to know, make the boat out of a metal that doesn't react with water? Wouldn't that be kind of an important thing? Because some metals react with water pretty violently. Now, when you look at your book, there's a little asterisk at the bottom of the chart. Right down here. Here's what it says. It says metals from lithium to sodium will react with acids and water. From magnesium to lead will only react with acids. So the top ones are the most active. They're able to react with water. And remember, we treat water as HOH in these reactions. So H can be replaced by acids, replaced in acids by everything higher. So anything that starts with an H and is not water, it can react with. So it starts with an H and it's not water. Everything higher reacts with it. Only the first four, lithium through calcium, react with water. And we know calcium reacted with water because we did that lab. We took a little piece of calcium, put it in the water, and it came out of the dish out of big foaming bubbles. So only the first four, lithium through sodium, will react with water. And you'll notice those are alkali metals or alkaline earth metals. So I want to show you what they mean by react with water and how some are more active than others. So got a video here. Okay, pretty grainy, but okay. So this is a piece of lithium. Okay, and you can cut lithium with an X-Acto knife. You've got to work at it pretty hard. It cuts. It's coated on the outside. It's shiny on the inside. Okay, but if you wait for a few minutes, that in just a few minutes, you'll see that the lithium actually reacts with, come on, 22, 23, come on, bring it back. Wait a few seconds. He's going to come back with that knife and see that it already reacted with the air in the time that it was just sitting there. That was real time. Here's what, oops, let's go back. I missed that. Come on, go move like a... Okay, so again, it got that coating pretty fast. Okay, now get some water. I'm going to put the lithium in the water. So you cut off a little piece of, oh, sorry, that's sodium. Didn't show the lithium part of it. So there's sodium, it's softer. Did you see it bend as he cut it? And this is potassium, really soft. And potassium reacts so fast that it's as fast as it hits the air. It gets new coating on top of it. Okay? So if I put some sodium in water, oh no, that's lithium. See lithium dancing around the surface? It's less dense than water, and it stays on top of the surface. That piece of lithium just floats there. Then you put sodium in. Sodium dances on the surface, but notice it's a little ball. That's because it melted. So it's a little sphere of liquid sodium dancing around the surface of that thing. Okay, when you put potassium, sodium reacts with water to make hydroxide and sodium. Okay, so that's sodium. Here is potassium. Potassium, when it makes the hydrogen gas, it actually lights it on fire. So this is potassium in water. If it gets trapped, it makes a little bubble, then it lights it and shoots it around. That was cesium. Oh, sorry, rubidium. Go back, rubidium. Working our way down. Okay. Rubidium. That was a little bit faster. Here's cesium. Oh, sorry, that's still more rubidium. Cesium, come on, cesium. There's cesium. Okay. So, as I went down the alkali metals, they got more and more active. Okay. And cesium, and what it is, it's about ionization energy. All these reactions involve the metals losing their electrons. Cesium hangs on to its electrons the least because it's got the most shielding. Okay. So when they say they react with water, that's what they mean. So you can see the list is longer. We would put all the alkali metals up here. They just didn't include them all because we saw them all react with water, except francium, and there's never enough francium for us to see. So Fe plus CuSO4. Is it going to happen? So we have to go find the, look on a table. So it's Fe plus CuSO4, and I need to find Fe and Cu. So I look at my table. Fe is here. Cu is down here. So Fe is above Cu. Fe is the senior, Cu is the freshman. So, is this going to happen? Can Fe replace Cu? Yeah, because Fe is above Cu. So the Fe is going to end up next to SO4, and the Cu is going to be by itself. Yeah.
So does that mean single replacement is not reversible?
Yeah, the single replacement doesn't reverse. Yeah. It lets you work real hard to put a lot of energy into it. You got to put as much energy into it as you saw coming out of it with that reaction. Okay. Right. So the only problem with this is I would have to tell you the charge on Fe because you don't know it. We can't look it up. On the other side, we still want to do the crisscross and look for 2s. Okay. So I'll tell you Fe is 3 plus and SO4 is 2 minus. So the 2 is going to go there. The 3 is going to go there. Does Cu need a little 2? Is Cu one of our diatomics? No. So now all you have to do is balance. So to get 2 Fe's, I got to put a 2 here. To get 3 SO4s, I can put a 3 in front of CuSO4, and I put a 3 in front of Cu. So that reaction is going to happen. And what I'd see happen is, remember the copper 2 sulfate was blue in solution, right? So what I'd watch is that blue color disappear, and then the solution would change color, and the bottom would be the color of copper. This is the test tube we did yesterday, where we did the single replacement with magnesium and copper 2 sulfate. Notice there's no more copper 2 sulfate up here because this is no longer blue, right? And the bottom is all orange, which is the color of copper. Okay? So it's not just words on a piece of paper. And it worked because magnesium was above copper, just like iron was. Okay. Okay. Pb plus KCl, lead plus potassium chloride. So Pb is a metal. It's going to try to replace a metal. Can Pb replace K? Yeah, because lead is here and potassium's here. Lead cannot replace potassium. Okay? Does that make sense? So the answer to this is no reaction. Al plus HCl, aluminum plus hydrochloric acid. Okay. Here's Al, and HCl, what it's going to try to replace is H. Can aluminum replace hydrogen? And the answer is sometimes. So what do you mean sometimes? Well, it's not one of the top 4, right? So it's above it. Aluminum can replace hydrogen if it's not in water. That's what the thing says, right? Because aluminum is not high enough to react with water on the list. So it's going to happen. So the Al is going to kick off the H. So the Al will end up next to the Cl. And H will be by itself. So I did the single replacement, one replacing. Now I need to do subscripts and formulas. Bless you. Al is 3 plus, Cl is 1 minus, so it's got to be AlCl3. Can H be by itself? Nope. It gets a 2. And then I would have to balance that. To get my 3 Cl's, I put a 3 in front of HCl, but that gives me 3 H's. You got 3 H's on one side, 2 H's on the other. That's an even odd problem. You solve that by doubling the first one. If I have 2 Als, that's got to be 2 AlCl3s, which gives me 6 Cl's. So I need 6 HCl's, and now I can balance that by putting a 3 in front of H2. So we got to that even odd problem, double the first one, see what happens from there. So we'd expect to see little bubbles of gas coming off of this. Al plus H2O. Okay, first of all, we want to write H2O as HOH here. In single replacement, we want to write it as HOH. Can aluminum replace hydrogen? Why, we just said yes, but now the answer, now it's in water. And hydrogen is different. Only the top 4 react with water. Since aluminum is not one of the top 4, this is no reaction. Otherwise, cooking in aluminum pans would be kind of silly. Because every time you cook with them, you react. And actually, when I told you I made pizzas for a living, the place I worked at made its own pizzas and made its own pizza sauce. So every day they mix pizza in a big stock pot. Well, after working there for a few years, I was making the sauce, and I noticed that there was sauce on the outside of the container. On the outside of the stock, so I wiped it up, and then I watched more sauce ooze out. There was a hole in our aluminum stock pot. And I looked at it, it's because tomato sauce is acidic. Tomato sauce is an acid. So the aluminum replaced the hydrogen in that acid, and that aluminum dissolved over time until it ate a hole all the way through a thick stock pot. Okay? So don't cook tomato sauce in aluminum containers, because tomato sauce is an acid. Don't drink your orange juice out of an aluminum cup. Orange juice is an acid. So what does it mean that silver's on the bottom of the list? What does the bottom of the list mean? It's not very active, right? It's always going to end up alone. It's always going to be the metal. The other things that go on the when you see the other ones that go on the bottom are gold and platinum. Gold and platinum belong down there. Why? Well, they don't react with very much. So think about what we use silver, gold, and platinum for. We use them for money. Up until the U.S., until we started getting paper money, there was a $10 gold coin was a coin that weighed as much as $10 worth of gold. That's what they meant by a $10 gold coin. Okay. And you want your money made out of gold and silver because gold and silver are not going to react. They're always going to stay by themselves. You would not want to put sodium coins in your pocket, because then when you did your laundry, you would no longer have any coins. Right? So you don't want reactive metals to make money out of. They also get used for jewelry, because you want it to stay a shiny metal. If it reacts with something, it's not going to be a shiny metal anymore. So if you've had that jewelry that turns your finger green, that's because it's not made out of silver or gold. It's got a little bit of copper or nickel. And those two both make green ions. And that shows you that you're doing a single replacement between the moisture on your body and the ring. So we use silver and gold as money and jewelry because we don't want them to change. Okay, those were metals. Yeah.
So if aluminum and zinc won't react with water, then how come they rust?
Aluminum and zinc don't rust. Galvanized steel is steel covered with zinc, so it doesn't rust.
Oh yeah, that's right.
And aluminum does rust, but the difference with aluminum's rust is a clear solid that actually coats. So if you look at aluminum furniture outside, it looks a little bit shiny, but if you scratch it, it's shinier underneath. That's because that thin coating of aluminum oxide that you're looking through makes it look dull.
Yeah. Well,
Okay. Yeah, aluminum alloys are different. That's just the mixtures with aluminum. Okay. So those were metals. What about nonmetals? Well, nonmetals can replace nonmetals too. But luckily for us, the list is shorter. We're going to limit ourselves to halogens, fluorine, chlorine, bromine, and iodine. And the activity order is the order on the table. So fluorine would be the most active and iodine the least active. Fluorine most active, iodine least active. Higher replaces lower. So F2 plus HCl. The first tricky part about this is recognizing what it's going to replace. Fluorine's a nonmetal. It's going to replace another nonmetal. So it's not going to take the place of hydrogen, it's going to take the place of Cl. Can fluorine replace Cl? Is fluorine above Cl? Yes, then fluorine can replace Cl. So on the other side, I'm going to have H next to F instead of Cl. And I'm going to have Cl by itself. Now we need to worry about little numbers. Does Cl get a little too? It's on column 7, so it's one of our diatomics. And H is 1 plus, F is 1 minus, so that adds up to 0. So I wrote the right formulas. Now I can balance. 2F, so I got to put a 2 in front of HF. That gives me 2 H's. I put a 2 in front of HCl. That gives me 2 Cl's, which I wanted anyway. So we're balanced. Br2 plus KCl. Okay, Br is a nonmetal. It's going to try to replace the nonmetal. Can Br replace the nonmetal in there? Because the nonmetal in there is Cl. Can Br replace Cl? No, because Br is below Cl, so this would be no reaction. So that's how we tell whether it happens. We look at the activity series for metals, and we look at the table for the nonmetals. And that's all I got. So on the right-hand side, do what the name says. Figure out the little numbers on the bottom. That's either crisscross or diatomic. And then bounce. That process hasn't changed. Okay. The front side is all single replacement. The back side is everything mixed together. So there's combination, there's decomposition, and there's single replacement. Let me write you a pass once a semester. We used them up.